Hi and welcome to Geeks for Geeks. Today we would be discussing the problem count elements in two arrays. Now in this problem we are given two unsorted arrays and each element of ARR we need to search the number of elements less than or equal to that number in ARR2 itself. So let us do the dry run for the sample test case. So we are given 1. So let's go and search the number of values in A22. 0 is less, so 1. 1 is less than equal to yes, so 1 more. Then 1 is also there, then 3. Then again 1, so 4. 4 values are there. That is why the answer to the first one is 4. Let's see for the next value, 2. So 0, 0, 1 is already there, 4 value is already there, then 1 more 2. So this value, that is why this value is equals to 5. Let's come to the values 3. So 5 would already be there. 5 elements would already be there. And then the next number of elements would be 3. Okay, so 3 is not there. So 5 would remain the same. The next number comes the 4. So the number of elements would be 5 plus the value 4, which is 5 plus 1, that is 6. Then we come to 7. So now, yes, it is told that given two unsorted arrays, but the first array is sorted. That is why we can just count the values and then we can add it. But don't get confused after seeing the sample test case, because it is told that it is not guaranteed that both the arrays would be sorted itself. Both the arrays are unsorted and we need to search the number of elements. So the first brute force approach that comes to our mind is that we can just do a linear search. Like for each element, we can just traverse the next whole array itself. So in the worst time complexity, we need to traverse all the element. So for one element in ARR1, we are doing M operation. So if ARR1 is having a size of M and ARR2 is having a size of N, then for one element in ARR, we would be doing N operation. So for M elements in ARR, we would be doing N multiplied by M operation. And in each element, we would just compare. So that is constant operation. So time complexity of this approach is N cross M. So can we do better than this or not? Yes, we can do better than this. So at what point do we need to do better? Like, what are the steps we are doing? Let's consider. First, we are selecting the element. Then we are searching the element. This is the step. Like we are getting the first element and then we are searching for the whole array. Then we are getting the second element and we are searching it. So let us think where we can optimize. See, selecting the elements for each and then trying to find the number of elements. Okay. So selecting an elements we need to do, because then how would we know that yes, for this element we need to find. So that particular character is required for the whole movie. So now the thing that we can optimize over is the searching thing. So we are using linear search here. Okay. Linear traversal. We are just traversing linearly. So what is a better search alternative than linear search? Definitely it is none other than binary search. So now we know that we need to do binary search. But as we know, binary search only finds an element. So how will it combat the array which has duplicates, and then it would count the number of elements? How would it combat this? So before trying to have this, let us first see that for the binary search to work, we need a sorted array. So the first approach, what we would be doing is, we would be sorting the array 2. Because for binary search, this is the first requirement that we need to do. So after this point, we would be learning an application of binary search. You can say that we would be learning an idea which would be based on the idea of binary search. So I suggest you to learn binary search if you don't know till this point, and then come back to the video so that you can understand it much better. Okay. So now we would be learning something as upper bound. So upper bound returns the first position where ARR of I is greater than equal to X. So let us quickly understand what do we mean by this. Suppose we are given an array as 1, 2, 2, 3, 4, and we do a upper bound of the value 2. Then it would return me this value. Now, suppose we do 1, 2, 2, 3, 3, 4, and then again we do upper bound of 3, then it would return me the first position where the value this is greater than the given value. Let us see some more values also. Like suppose we do a upper bound of 5 and we do 1, 2, 2, 3. So if we do upper bound of 5, it would position to the last element, after the last element. So if an element greater than the target is present, it would return its first occurrence. Else, if it is not present, it would return the position after the next position. So now we can use upper bound to calculate the number of elements less than or equal to. How would we do it? Let me show you that also. Okay, so now first what we would be doing is, as we would be doing an upper bound on the ARR2, so we would first need to sort it. So after sorting it, it would become something like this: 0, 1, 1, and 1, then 2, and then 4. And now enumerating the indexes are 0, 1, 2, 3, 4, and 5. So now let us do an upper bound and let's see this in action. Suppose we do upper bound of 1, then it would point to this location, that is 4. And yes, 4 is the answer. Now let us do an upper bound of the value 2 and it would point to this value. And yes, 5 is the answer. So now let us do an upper bound of the value 3 and it would again point to this value and 5 is the answer. Now let us do an upper bound of 4 and it would point to the value after that, that is 6. So yes, 6 is the answer. Now same goes for 7 and 9 where it would point to this element and that is greater than that. So if somehow we learn how to implement upper bound on our own, then we can easily solve up this problem. So now let us see how do we implement upper bound. So as I have told you that upper bound is based on the idea of binary search. So we would initialize a low as 0 and high as the last index, that is 5, the range to be found. So initially mid will be equal to 0 plus 5 divided by 2, which is 2.5. Doing the integer division would make it 2. So now let us see 30. So now upper bound of 30. So now this element is not the element we desired. Why? Because our answer would definitely. So the value given than or equal to. Elements are greater. So we would need to go on the right hand side. So now going on the right hand side, we would make low is equals to mid plus 1, that is 3, and high would remain the same. So now in the next iteration, we would have 3 plus 5 divided by 2, which is 8 divided by 2, that is 4. Now we compare 4. So the value at 4, which is 40, yes, that value can be a potential answer. Why? Because this value is greater than that. Okay. So first we would save this value and we would say answer is equals to 4 as of now. Okay. And then we know that going on the right hand side is not our thing. Why? Because we need the first occurrence where it is the next greater element. So if suppose now the current element is the greater element, then going on the right hand side solves no purpose, because on the right hand side we won't find the first occurrence. So for the first occurrence, either this element is the first occurrence or the first occurrence would lie on the left hand side. So if the first occurrence lies on the left hand side, so we need to make high at that side. So high is equals to mid minus 1, that is 3. So now 3 and 3. So now 3 plus 3 divided by 2, which is equals to 6 divided by 2, that is 3 itself. So let us compare the value 3. So if we compare the value 3, then again 30 is less than that. So now this time again low would be mid plus 1. So now we would be doing again the value 4. So now 4 and 3. At this point, low is becoming higher than high. That is why we would be saying that at this point, we won't be doing anything. So now let me first tell you how this is happening. So now let us talk about the intuition too. Suppose this is A1, A2, A3, A4, and A5. So this is the first point, or this point is the answer. So now it can be a scenario that suppose we are standing at this point. So either this is the answer or the answer would lie here. Suppose we are standing at this position. So going at that position would have the elements greater than that. That is why we are tend to move on the right hand side. So if A of mid is greater than the target, we tend to move on the left hand side. So moving on the left hand side means that high is equals to mid minus 1. If moving on the right hand side, suppose we get an element lower than that. So if we go on the right hand side, that means we would getting element more lower than that. So we need to go on that side. So if A of mid is less than or equal to the target, because this is not the answer we desire. So we would say low is equals to mid plus 1. So just try to visualize this, do it for pen and paper and you would understand this. So now what we would do is we would first sort the second array and then we would use upper bound to implement this. So now let us move to the coding part and you would understand it much better. So now we have the array here. So what we need to do is we need to first have a vector int of res to store the answer. Then we would sort the value. So we need to sort the values, that is arr of 2 comma. So arr of 2 comma arr of 2 plus n, because the second array has the size of n. Now we would need to iterate for int I is equals to 0, I is less than n, and I plus plus. Now at this point, we need to do the upper bound of the element. So let us quickly do that. So we would be returning an index. So the return type would be int, and then we would be saying upper bound. Okay. And then we would be taking the parameters of the array itself, then the size and the element to be found, that is x itself. And then we would be initializing the answer as n, because we told that if the answer is not found, then the answer is last element plus 1. Last element plus 1. So here the last element's index is n minus 1. So last element index plus 1, n minus 1 plus 1 is equals to n. That is why the initial answer is n. So we would have low is equals to 0 and high it will be equal to n minus 1 itself. Then we would be going down and we would be saying while low is less than equal to the high itself. And then we would be saying int mid is equals to low plus high divided by 2. And then we would be saying that A of mid, if the current element is greater than the value x, then yes, this value can be a potential answer. So answer is equals to the value mid. Okay. And then we would be saying that high is equals to mid minus 1, because this is the answer or this can be the answer, but the elements on the right hand side can never be answered. So we tend to move on the left hand side. That is why mid minus 1. Okay. So then we have the else condition where a of mid is less than equal to the value x. Please remember this at this point. And we would be saying that low is equals to mid plus 1. And this can't be potential answer, so we won't be updating the answer also. At the end, what we would be doing is we would be just returning the index. Now we just need to call it. So at this point, what we would be doing is int index is equals to the value of upper bound. So what we need to do is we need to call for ARR2, that is what we have sorted, and then the value n, and then we would move forward to ARR1 of the I itself. And then what we would do is we would just simply push it. So push back and then the index itself. And you can directly push back. You don't need to save it in the index variable. I'm just doing it for the clarity so that you would understand it much better. And you would just return the rest value. Let's just compile and run and see how many mistakes are we making. Okay, we are not making any mistakes for the sample test case. Now let us talk about the time complexity of the solution. At this point, we are doing n log n operation. And here, for each of the element, we are trying to find the element of the upper bound. So upper bound, as in the binary search also, we are dividing the segment by 2 at each iteration. So upper bound has a time complexity of log base 2 n if the size is n. So this is log n, okay, and this is it. So time complexity would be m log n, and the space complexity would be big O of n if you consider this res array, or else if you don't consider it and it is already given, then this is big O of 1. Now, if you are here till this point of the solution, consider liking the video and commenting understood or 1 in the comment section so that the reach of this video could be increased. Thank you and have a nice day.